Dear Level 3 students, credit our system, Department of Socio-Computing at the Faculty of Economics and Political Science, Cairo University. Welcome back to our course named Social Network Analysis. Lecture 15. Hello. Let's start as usual by a brief review of what we have studied in the past or previous two lectures, because this lecture is based on what we have studied in the previous two lectures, which are lectures 13 and 14. In the first 12 lectures of the semester, we studied network analysis from a static point of view. What's the meaning of a static point of view? This means that we studied network analysis or social networks as not changing with time. So we took like screenshots from the social network, and then we calculate some measures upon which we build our analysis. We studied many concepts in static network analysis, but starting from lecture 13, we started a new part in our course, which is dynamic network analysis. And we said that in real social systems, networks are never static. Networks are always changing, continuously changing. So we started to study dynamic network analysis, and in lecture 13, we said that there are three basic questions you have to ask yourself if you are going to study dynamic network analysis. The first question was, how do networks evolve? And we studied the dynamics with which network evolve with time, and we say that we have two interpretations of these dynamics or continuous dynamics occurring inside networks. These two interpretations, namely the diffusion, which is contagion or the spread among the networks or the nodes of the network, and we studied that this is a very a very familiar social phenomena, which is diffusion, and we say that the diffusion is like contagion, but not in the biological or physiological sense. We talked about thought contagion, and that people tend to imitate each other, and this is why some changes occur dynamically in a certain network or social network with time. So this is one interpretation of how do networks evolve with time. The other interpretation is the homophily principle, which, as you remember from the previous lectures, homophily means that similar people tend to be together or tend to communicate with each other more than dislike people or people who are not similar to each other. So, based on the homophily principle, also networks change with time because people tend to communicate more with people who are more similar to them, and when they find similar people, they go and communicate with them. So the links and the connections or the social ties changes with time inside this network. So yes, networks evolve, and yes, social networks are dynamic, and in order to make a valid analysis for social networks, you have to put the dynamic aspect of social networks into your consideration. And answering the first question, which is how do networks evolve, we have two interpretations, which are the diffusion and the homophily principle. And then we say that we have two other questions that may elaborate more the answer of the first questions. These two questions are, how can we predict what kind of network will form? Since networks evolve, then we need to have a facility that lets us predict what kind of network will form with time. And the third question and last question, how can we predict what will happen inside the network? Diving into the second question, which is how can we predict what kind of networks will form. In lecture 14, we said that there are we will study four kinds of social networks, which are random networks, scale-free networks, and small world networks, and happened-spoke or star networks. And in lecture 14, we started with the random networks, and we saw how the random networks are very important and very crucial in order to understand how networks evolve and in order to predict what kind of network will form. In today's lecture, we will continue to study other kinds of networks, which is a scale-free network. In order also to, I want to remind you that we are studying these specific kinds of networks. Why? In order to answer our second question, which is how can we predict what kind of networks will form with time. So let's start today to discuss scale-free networks, but before discussing scale-free networks, I want to ask you some questions. Do you remember what we have talked about in the previous lecture, which is random networks? Do you remember Erdős-Rényi networks? I will give you, yes, I hope I can hear you now. Yeah, Erdős-Rényi networks were uniformly distributed networks in the sense that we have certain number of nodes and certain number of links, and then we spread these links among the nodes in a uniform distribution. However, there are not only uniform distribution networks just like we have the Erdős-Rényi networks. There are other ways even to grow networks. So random networks is not the only way to grow or the only methodology or the only technique in order to grow networks with time. There are other ways to grow networks with time and to make networks evolve. So, for example, what happened at Erdős-Rényi networks is that, as I had talked before about it in the previous lecture, we had a stable number of nodes, and we denoted it by n, and we threw a stable number of links, which we called capital M, and we just threw these links among the nodes, or we distribute these links among the nodes in a uniform distribution. So these links are uniformly distributed over with a certain probability, and if you remember, we talked about probability P, which is the probability that this node will have a link. So if I have 5 nodes, for example, and 3 links, then each of the 5 nodes have the same probability that this link will lie or will be connected to it. If I have only 3 links and we have 5 nodes, so all 5 nodes have a probability of 3/5, for example. This is not my concern now how to calculate the probability, but my concern is that each node has the same probability of growing a link with time. This, what we have studied, or this is the Erdős-Rényi way of growing networks or dynamic networks, which we called random networks. And we say random networks because the links are randomly distributed among the nodes with equal probabilities. So that's what we had until now. Now I can also change the number of nodes. I can increase the number of nodes in another mechanism of growing a network. And I can start that very simply by adding network with a uniform likelihood or probability. I would start, for example, with a certain number of nodes and a fully connected network, and then I add new nodes with a certain number of links, and these links connect to these existing nodes with a uniform likelihood. Imagine, for example, that let's say there is a cool table inside the college cafeteria, for example, and there are a certain number of students sitting on this table. And a new student now comes in and joins them in this table. This new student, during his lunch break or her lunch break, can make 3 connections, and these connections then are with uniform likelihood, a third with equal probability, kind of reaching out to these existing nodes or students on the cool table. After that, another student comes in and joins the same table. The same thing happens here. Can you say already something about the dynamics, for example, over time? Who will have more connections or nodes than others? So again, let's suppose that there are 3 of you sitting on a cool table in the cafeteria. And we say this is the cool table because this is the table for cool persons and for cool friends, for example. So 3 of you are sitting on this table and you are having your lunch together. So the 3 of you forms a network, and there are connections between the 3 of you because the 3 of you are friends. Or we can say that you are triadic here. The triangle is connected to each other. And then let's assume that another newcomer student come and join your table. And this student or this newcomer student have a chance to make only 2 connections through this lunch break. Which 2 of you are 3, okay? So you are 3 students and there is a newcomer which has only a small chance during the lunch break, so she can only connect with only 2 of you. So which 2 of you will be probably the connected nodes to her or to the new comer student? So can you already say something about that? Can you predict over time who of you have more connections or nodes than the other? The people who were first or the people who came in later as a general tendency? Who will accumulate more nodes with time? Yeah, I want you to think with me. Who will accumulate more nodes? I say that you are 3, and then there is a newcomer, which is the 4th person, and then there is another newcomer, which is the 5th person, and then there is another newcomer, which is the 6th person. So, who of these 6 persons will accumulate more nodes time or more connections with time? Well, yeah, the older nodes will have more links because it's a uniform likelihood. There is an equal probability that I would connect to the new person by just random chance. So let's say the 3 or 4 students that were there first at the pool table, they will accumulate more, where the people or the newcomers will just who just came in has actually no connections made yet, and they will have a certain probability to make connections than the older people, because the older people meet more than the newcomer. So if you have been there before the newcomer, you may have received more connections on average. So we can make some predictions about how these kinds of networks evolve with time. This is regarding the examples that we have just discussed now. But now, these connections don't have to be with uniform likelihood. And actually, in reality, it almost never happens with uniform likelihood, because what we find in reality, if we look at real social networks particularly, that also happen in other networks like neural networks or infrastructure networks, that some nodes have many more links than others. And actually, what we often find is that few nodes have many relationships or many social ties and connections, and many other nodes have very few connections. So there are many nodes, really many, that have done like one or two connections only, and there are very few nodes who have a lot of connections. And we call these nodes hubs. Do you remember the hubs in the previous lectures? So, in real social networks, the connections or the links are not uniform. They are not with the same probability. Or if we have a new node or a newcomer student, in real world, no, it's not the same probability for each one to grow friendship with this person. So in real world, you will find people who have many connections and who are the stars or the hubs of the society, and many other people having a very few number of connections or even just one connection. This phenomena is often called the fat tail distribution, or the technical term of this, it's a power law of statistical distribution. Now, the mechanism how you create such an unequal power load distribution is also distributed according to the same effect. We find people in a society that have, for example, much income, a lot of income, and we find many people in the same society that have very little income. So that's also what we call power law. It's also called the Pareto distribution. If you have economics or if you studied economics, for sure you might have heard of this. This is the same logic. So, how is that created? It's created by what we call a preferential attachment in a network. The result is this scale-free network. The results are called scale-free because if you have a power law, yes, there are scale-free. It doesn't do. If you zoom in and out of this scale-free network, you will find what it called fractals, and we don't have time now to go into that or the concept of fractals, but we will discuss the concept of fractals at the end of the lecture. So it means that the scale-free networks means that independent from the scale that you will get from the network, it looks very similar. So now, what's the meaning of preferential attachment? Because this is a very crucial characteristic that creates scale-free networks or creates these kinds of networks in which there are only few people having the majority of the links or connections or social ties, and many other people having very few links or connections or social ties. These kinds of networks are called the scale-free networks, and the scale-free networks are grown using the concept of preferential attachment. So what the meaning of preferential attachment? Preferential attachment means that the likelihood that you connect with somebody is proportional to the number of existing degrees. Do you remember degree centrality? Do you remember what the meaning of degree? Yeah, the meaning of degree is the number of links or connections a node has. So, preferential attachment means that the more nodes or the more degree you have, which means the more nodes you are connected to, the more probably you will be connected with a new node, or that the likelihood that you connect with somebody is proportional to the number of existing social ties and connections you have. So that means that the person who already has a lot of connections, it's more likely to receive another connection. There is a preferential attachment to this person who has a lot of connections already. And we often see that in reality. To go back to my example of the cool table in the college cafeteria, the most popular student that's on this cool table has already a lot of connection, and you most likely will be drawn to this person too. People are drawn to the most popular student. So the person who has a lot already will get more. Almost like some quotes that says the rich will get richer and the poor will get poorer. That's what preferential attachment is. So that's who already have will be given more. Who already have social connections, who already have many friends, who already have many social ties, who already have many communication will be given more and more social ties and communications. And those who have nothing, even the social ties or communications they have may be taken away from them and going back to the person who is most popular. That's the idea of preferential attachment, and this is also called Ewald's rule. But I prefer the term preferential attachment because it's more clear than the name of the rule. And so this is the idea of preferential attachment, and how can we do that formally. I will talk now about the formalism of this intuitive theory. But if your intuition is fine, and if you understand the basic concept of preferential integrity, that's also fine. So you don't need to have or to study the formalism of this theory. I just want you to understand the main concept of preferential attachment. So now let me walk you quickly through the formalism of this theory. So if there are new nodes, and every new node adds m links, certain number of links to existing nodes, therefore at time t, every time t that happens a time step, there will be t times m links. For example, if we have 5 nodes, and then I have a new node which is the 6th node, the 6th node will add a number of m links to the existing networks, because the new coming or the newcomer node or the new node will make some connections with some people already existing in this network. So it will add more m links to the network at each time step. So at each time step we have t, so overall we will have t times m links. So the total number of degrees is t times m times 2, because in each link there are basically 2 degrees for the 2 nodes connected with this link. So that is the formalism of how you can grow these kinds of networks. And as I told you, if you understand the basic concept of preferential integrity, you don't have to study this rule by heart or to memorize it. I just want you to understand the basic concept of preferential integrity, because this is the main technique with which scale-free networks are grown. Now, let's start by growing some scale-free preferential attachment networks. We talked about the main concept of scale-free network, and we talked about preferential attachment, which means that nodes who have more connections with other nodes, or nodes who have high degree centrality, are more likely or more probable to have more nodes connected to these nodes. because in real world, people who are more popular are more likely to grow new connections with other new people. So now, after we have studied the basic concept of preferential attachment, which means that you prefer to be attached to the most popular people, and so the network that will grow with time through this preferential attachment principle will be called the scale-free network. After studying this concept, we will now try to like experiment it with the NetLogo software. Do you remember NetLogo software that we have talked about before? This screen shows the screen of a NetLogo experiment where at the right hand side you will see the visualization of a network, and at the left hand side there are some of the measures, mainly the degree distribution measure, which we will talk about today. I start here with two nodes, these two red nodes in the black area. Do you see them? I start here with only two nodes, so there are only two nodes in this network. And preferential attachment says that there is a likelihood that a new node comes in and connect to these nodes. Let's say now the connection is 1, which means that if a new node comes, it will create only one link. This is what we just defined. However, it could come with two links, but in this case, we just defined the new node to come with one link. So we have in our network, the old nodes are just two nodes, or the eldest node in the network are just two nodes. Let's say that these are only two students who are sitting on the table in the cafeteria, and then a third node will join, but this third node will form only one link. So the new node will choose either to grow this link with the first node or the second node with the same probability now. So there is an equal likelihood it connects to each one of them, because each one of them is equally likely till now. Till now they are equally likely because they are only two nodes and only one link. So these two nodes are of degree 1, yes. So each of these two nodes have the same degree. This means that each of these two nodes have the same probability that the new node will grow a link with them. So let's do that as throwing a new link, and when you connect to that one, and we throw in another link and it gets connected to the middle one. So what we have now is the middle node. As you see at the right hand side in the black area, we have a middle node, and I show you where that by increasing the size a little. The middle node now has 3 connections, as you see. So we have 4 nodes now in the network. The middle node has degree 3, and each of the other 3 nodes have degree 1. So proportionally, it's 3 times more likely. So the middle node is 3 times more likely to get a new connection now than the other 3 nodes. That means that the other 3 nodes can still get a new node coming in and connecting. Somebody could connect to, like an outsider, for example, but with more likelihood it will connect to the one who has the highest connections or the highest number of connections. So it's proportional. 3 times could be, or there could be another rule of how proportional it is, and we can see here in this graph. This graph is very important. Keep on watching this graph. At the left hand side of the screen we can see there is actually one node with this way goes the number of degree. So one node with 3 degrees and 3 nodes with only 1 degree. On the x-axis is the number of degrees, and on the y-axis is the number of nodes with this degree. So here in our example we have one node with degree equal 3 and 3 other nodes with degree equal 1. That's how you read this graph, and it's very important because it gives you an idea about the degree distribution, how degree is distributed among the nodes inside this network. Let's keep on going then and throwing another node and then connected to an outsider and then throwing another node and then throwing another node. What I see is still the chance that connects to an outsider, or now it can be connected again to the main hub. We can see there is one outside and actually also gain some probability of being connected. Now, the NetLogo application keeps on connecting and keeps on collecting and keeps on accumulating and gets bigger and bigger and bigger. It gets, and the bigger it gets, you will find that the rich will get richer, like, right? As you remember from the previous style, the middle node has 3 degree of 3 and the other 3 nodes have degree of 1, and this middle node, which was rich in the degrees, get richer now because it's getting bigger and bigger. As new nodes are connecting and joining this network, they tend with a more probability to join this middle node because it is the one with the most or the maximum number of links or social connections. It's like the most popular node here in our graphs. So again, those who have more links will be given more and more links. And that's what actually happens in reality. There are some little hubs outside. You can also see here in this network at the right hand side that there are also some little hubs outside the connections of the middle node. They also make some friends and they also are becoming popular, and sometimes somebody connects to them. But if you look at the graph actually at the left hand side, what also happened on the graph is that there are very few nodes who have a lot of degree. So even these hubs are very few in numbers. Yes, we don't have just only one hub, which is the middle node. Yeah, this is the maximum size or the biggest hub. But there is other hubs. But what are the count of hubs here? There are very few nodes who are hubs or who have a lot of degrees or a lot of connections. And most other nodes actually have only one connections. So most nodes have only one connection, and only few nodes have a large number of connections in this network. So most nodes actually have one connection. There are some other hubs, as I said, or sub-hubs, smaller hubs, that are in there in the graph, as you see when we run the program again and again. But they are very few nodes who are or who can be considered as hubs. Actually, it's one big node or one big hub which has the maximum number of connections or the highest degree centrality. One popular student that actually keeps on accumulating connections with newcomers and becomes more popular and more popular and more popular. So at the end, we have now, do you see here at the left hand side, we have 200 nodes, as you see in the graph. And as you see, the most of these 200 nodes actually have only one degree. And there is one node here in the center that has more than how much? 70 degrees. So one node has 70 links or connections, and the majority of the 200 nodes have just one connection or one social tie. So that is the richest one, and actually started with a path dependency. What the meaning of path dependency? The path upon which this network evolved to the shape that you see now depends on what? Depends on how popular this node was at the beginning. Because if a node is more popular or having more number of links from the beginning, then it's expected that at the end of the simulation or at the end of the evolution of this network, the path to which this network evolved will depend on the initial conditions, which means that initially which node was having the most probability or the most number of or the highest number of links or connections. It started right from the beginning, when actually just this node was lucky to receive more nodes and more connections. And remember, the beginning there were only two nodes. Each one of them could have been in, and then came a third node. And the third node made one connection with one of these two. So the person who was connected to the third one now have a degree of 2, while the other two have a degree of 1. So if there is another fourth new node come, it will be more likely to connect to the node with 2 degrees, and so on. So it was lucky enough from the beginning to receive more nodes, and when it received more nodes and more connections, the path depends on this, and it gets bigger and bigger, and it gets richer and richer, and so on. Each one of these three could have been most popular, but then at the end it started to set it in a path dependency, which then determined this outcome. And that's what often happens in this kind of mechanisms. Now let's do that again. Let's do the same experiment again and reset everything from the beginning. To see, let me start again with our two nodes and add another node. We have now here like a hub already that we can see, but we have several hubs that I see. We have one in the middle, and there is some other hubs growing around there. So in this case now we have 1, 2, 3, 4, 5, 6 hubs. We can count them. 6 hubs here at the right hand side, the visualization of the network. They are clear to be, it's clear that this network has around 6 hubs. We rolled the dice, and it might have been unlikely that the most popular students get the connection, and there is still a probability that's what happened in this case, and now we have several hubs. So, do you remember the shape that emerged in the previous slide? In the previous slide, we had just one big hub, and there are 2 or 3 other smaller hubs. But in this case, when we made the experiment once again randomly, we get new outcomes, and the emergent phenomena here is different than the emergent shape or the emergent network structure. And we say that the network evolved into a shape in the previous experiment, and it evolved into another different shape in this experiment where we have several hubs. Now look at our graph at the left hand side. The average degree distribution is still this power law as well. So still there is very much inequality where we have very few. It might not be 1 in this case, it might be 3, 4, 5, or 6 hubs, as I said. that have a lot of connections, over 20, 30, or 40 connections maybe, and there are many, most nodes actually still have just one connection. So now we get, or we grow network in a different structure. So we get different network structure from the same initial conditions of the previous experiment. Therefore, that kinds of networks, or the network we see now at the left-hand side of the screen, network A or shape A, it's not a random network. Do you remember random networks or Erdo-Shreni network? Do you remember the shape of them that we discussed at the beginning of this lecture? The Erdo-Shreni networks are random networks, but the shape that you are seeing now, the shape A here, it's not a random network. It's not random in sense of the uniformly random probability of how we connect them, but we get these hubs. These hubs that connect to many other nodes, and we have an extremely unequal degree distribution. A degree distribution is distributed according to a power law. Exponentially, few nodes have many connections and many nodes have few connections. So if you take, for you who are interested in and work with logarithms, if we have statisticians here or mathematicians, so if you take the logarithms of both sides, the degree and the number of nodes, you get a straight line as the one you see at the right hand side, or shape B here. You can see here you get this basically a straight line on a log-log plot between the degree and the number of nodes. So you get a straight line in a log-log plot, which is the signature of a power law or a scale-free network. What's the meaning of the signature of a power law or scale-free networks? It means that when we see the degree distribution to be exponentially unequal like this, and only few nodes having the maximum number of links, and the majority of nodes have only one or two links. So this is like a signature of scale-free networks. We know now that these are called scale-free network. Now and finally, for those of you who are interested why this word scale-free, why we use the word scale-free to describe these networks. I will just clarify the concept, but it's just only for you who are interested to understand the concept of fractals that I talked about 2 or 3 slides before this slide, and I told you that we will discuss the concept of fractals in the new slide, or the final slide here in our presentation. So we call it scale-free because if you keep on growing and growing this network, you will get a very big network. And if you look like you see the network at the left hand side, this is maybe the network after 2 or 3 time steps. But if you keep growing and growing the network, it will be with the shape that you see at the right hand side, the bigger network. And if you look at these big networks, if you get some hubs, and then if you zoom, for example, take one of your favorite subclusters here, some of your favorite sum hubs, and you zoom in on that sub-hub, you will see a self-similar structure. The same structure is shaped again. These are called fractals. So fractals tend to form in scale-free networks, and we say that scale-free networks resemble the real social networks. So in real social networks, fractals also tend to form. Also, there will be one big hub with a smaller hub and a smaller hub, and then you zoom in again depending on how big your network is, and you will see the same shape, one big hub which is connected to one small hub and another small hub and so on. Some big, some small, also independent of your scale. The network will always look like that. That's why it's called scale-free networks, because regardless the scale you are zooming at, the network will always look the same shape or the same structure. And scale-free networks are grown. How? By referential attachment. So do you remember what is referential attachment, which is the main principle we talked about today? And we said that it is the main principle behind growing scale-free networks. So I'm asking you, what is referential attachment from your point of view? And I hope you liked this lecture, and I hope you understand the concept of preferential integrity, preferential attachment, scale-free networks, and how to formalize them. For any further question or for more communication, please don't be hesitated to contact me on my email on the screen now. And you can also view these lectures on my YouTube channel or the YouTube channel of Cairo University as well. So waiting forward to hear from you soon. Thanks.